So the last lecture is, I think, fun. It's talking about respiration under unusual circumstances. And this is a lot of kind of reviewing things and understanding how the system that we now understand, how it will work when it's challenged in different ways. Okay, so let's just start off with a few, I want to just mention a few breathing terms. Hyperpnea, hyper is kind of an increase, pnea is breathing, so increased ventilation. Hyperpnea, you increase ventilation due to increased metabolic demand, and so you've matched ventilation with metabolism. Hyperventilation is similar. You have increased ventilation, but with hyperventilation, you are ventilating more than metabolic demands, and you will blow off CO2, producing hypocapnia, low PCO2. Hypoventilation is ventilation that's not sufficient to meet metabolic demands, and this will result in hypercapnia, so CO2 retention. Eupnea, you're breathing just right. Tachypnea is rapid breathing, okay? And I always visualize Sigourney Weaver in Ghostbusters, you know. Anyway, you have to be there, I guess. Ataxic breathing is uncoordinated, irregular breathing. Dyspnea is a very common feature of many respiratory diseases. This is a subjective sensation. You feel like you're not getting enough air, okay? And it could mean any of a number of things, and people will not exercise because they feel dyspneic. Okay. Orthopnea is dyspnea that occurs when you're lying down, but it's relieved by propping yourself up, and people talk about three-pillow orthopnea, and if you're lying down, you can't quite breathe, but you feel like if you're propped up on three pillows, you can. If you think about houses in the Middle Ages, a lot of them had what were called bed chambers that were too short to even lie down in, so people would sleep pretty much sitting up, and maybe most of them had edema or something, and so, I don't know, whatever. So that's orthopnea. Okay, well, here's ataxic breathing, cluster breathing, gasping, okay? And there's kind of an interesting one called Cheyne-Stokes breathing, and these are periods of waxing and waning hyperventilation interspersed with periods of apnea, or no breathing. Okay, and this is thought to result from a delay in the feedback system between arterial PCO2 and the central chemoreceptors. Okay. Now, if you have a delay in a feedback system, okay, this is an example would be you're driving on the expressway and your car is starting to veer off to the right. You don't like that, so you turn the steering wheel to the left. So if you have an old car and there's play in the steering wheel, you turn the wheel, but nothing happens. So you turn it more and nothing happens, and you turn it even more, and then now suddenly you start shooting off to the left, and so you have to turn to the right, and so you're kind of overcompensating in both directions. So Cheyne-Stokes breathing is seen in normal individuals sometimes when they're sleeping at high altitude, and another situation is congestive heart failure, where the heart is pumping the blood, but it's moving pretty slowly, okay, and so it takes a long time to go all the way through the systemic circulation and through the pulmonary circulation, okay, and so let's say we start with the period of apnea, okay, so we have gotten the arterial PCO2 up to a high level, and so this starts triggering hyperventilation, so then you're blowing off CO2, and you get the CO2 lower than you would like it to be, but by the time the blood gets around to the central chemoreceptors and they respond, you overcompensated. Anyway, that's Cheyne-Stokes breathing. Okay, now we'll talk for a few minutes, quite a few minutes, about high altitude. Okay, and this is a really interesting situation, and the main thing about high altitude in terms of the respiratory system is you're breathing air with a low PO2. Okay, so In this graph, we have atmospheric pressure, barometric pressure on the x-axis going from 0 up to sea level of 760. Then on the y-axis, we have altitude either in feet or meters, whichever you prefer. And then on the x-axis on the top, we have inspired PO2. Okay, so if we go to Denver, Mile High City, so about 5,000 feet altitude, and for some reason these little symbols are not on the curve. It should be up here a little bit. Anyway, barometric pressure is close to 600, so it's a lot lower than at sea level. At sea level, PiO2 was 150. It's more like 120 or 125 in Denver. Okay. Now, here's Pikes Peak, and here we have the highest human habitation, around 16,000 feet elevation, and barometric pressure is below 400. And the inspired PO2 is around 70. Okay, then Mount Everest is the highest point on the surface of the Earth. Barometric pressure is a little over 200, and PiO2 is between 30 and 40. Okay. So when you have low barometric pressure, the gases, the partial pressures of the gases are scaled down in proportion to their what proportion they are. So the way you can, so then let's calculate inspired PO2. Okay, so the inspired PO2 is barometric pressure. Then we have to subtract off the water vapor pressure because we breathe the air into our trachea, we warm it to body temperature and humidify it to 100%. So now all the way from here on, you're going to have 47 torr of water vapor pressure. You can't do anything about it. Okay, so we subtract off the water vapor and then we multiply the result by FiO2, and that gives us PiO2, partial pressure of oxygen in inspired air. Okay, so at sea level, we have our kind of standard case. Barometric pressure is 760. We subtract off 47 water vapor and multiply that by 21%. And so PiO2 is about 150. Okay, let's go up to 18,000 feet. And this is a little bit higher than the highest human habitation, but you can certainly go up there if you feel like it. Barometric pressure is half what it is at sea level. So PiO2 is 380, barometric pressure, minus the same 47. Okay, even though the barometric pressure is lower, the partial pressure at body temperature of water vapor is always 47. So that's going to stay the same. And we multiply the difference by 21 and we get 70 torr. Okay, so the inspired air is 70. Okay, so this is going to have effects. And one more example, let's go up to 63,000 feet. And you can't do this on the surface of the Earth. You have to go up in on an airplane at very high altitude, and you probably don't want to try to breathe without wearing some kind of a mask or something, because PiO2 is barometric pressure minus water vapor pressure. That's 0 times 0.21 is still 0, so you get 0 oxygen into your lungs, because the air that you're breathing, the air inside your body will be just water vapor, and there's no room for anything else. Okay. So here we're looking at the partial pressure of oxygen at different points in the system. At sea level, PiO2 is 150. In the alveolus, it's about 100. In arterial blood, it's about 95 because there's a big A, little a difference, an A difference. Then the body takes out oxygen needed by the systemic muscles and stuff. And so venous blood has some low PO2. Okay, now if we take the case of someone living at 15,000 feet elevation, okay, their PiO2 is about 80. The alveolar PO2 is maybe 45. Arterial blood is maybe 44. And then venous blood is going to be lower. Okay. Now, even though these two people are metabolizing at the same rate, the PO2 changes more in the person at sea level than at high altitude because this person is operating in the steep part of the oxyhemoglobin dissociation curve. Okay, and this person is starting kind of where it's flat and then coming down, if that makes any sense. Okay, so when you go to high altitude, if you rapidly go up to high altitude, you can get acute mountain sickness. And acute mountain sickness is not caused by high altitude per se, it's more by rapid ascent, okay? And most of the acute mountain sickness symptoms go away after a week of acclimatization, or maybe a few weeks. There are things that do change and you never recover, okay? So, but the acute mountain sickness symptoms, dizziness, fatigue, confusion, headache, insomnia, malaise, possibly edema in severe cases, and unconsciousness, okay? And the edema is due to hypoxic pulmonary vasoconstriction, which will happen without fail in everybody who goes to high altitude. In some people who are maybe more sensitive, it causes edema. In other people, it doesn't. Okay, so the pulmonary edema is the leading cause of death in people who go to high altitude. Okay, and this is kind of the higher you go, the more symptoms you get and the more severe things are. Around 2 kilometers, say Santa Fe, Colorado Springs, 10 to 20% of the people will get acute mountain sickness. Okay. One side of my family has family reunions every 3 years, and we used to always go up to the mountains in Colorado, but 2 or 3 people get acute mountain sickness, so we can't do that anymore. Anyway, 4 kilometers, Mauna Loa, La Paz in Bolivia. Half of the people get acute mountain sickness, 12 to 18%. It's severe, and 2 to 3% of the people die as a result. And go to the Internet Cafe on Mount Everest, 5,300 meters, and more than half the people there have acute mountain sickness. Okay, most of the symptoms of acute mountain sickness are prevented by slow ascent, just go up 1,000 feet per day. And if you don't have time to do this and you want to get up there and start skiing, you can take nifedipine, it blocks calcium channels, and this tends to inhibit hypoxic pulmonary vasoconstriction. But the treatment for acute mountain sickness, immediate supplemental oxygen and rapid descent. Or you can put them in a hyperbaric chamber if you have one and give them elevated oxygen. Okay, now there are 4 main kinds of responses to high altitude. Okay, and these responses are hyperventilation, and we'll talk about all 4 of these separately in the next couple of minutes. Okay. The next response is polycythemia, produce more red blood cells. Okay, there's a right shift of the oxyhemoglobin dissociation curve, and finally we get to actually use 2,3-diphosphoglycerate, DPG being one of the 4 things that shifts the oxyhemoglobin dissociation curve to the right. And finally, we have hypoxic pulmonary vasoconstriction. Okay, now all of these responses happen, and they take from days to weeks to come to completion, and all of them have at least some part that's beneficial, but they all have downsides as well. Okay, so let's look first at hyperventilation. Okay, well, you hyperventilate because there's a low PiO2, the air has not much oxygen, your inspired air has low oxygen, your alveoli have low oxygen, and your blood has low oxygen, okay? So the peripheral chemoreceptors detect this because they are really keyed in on responding to oxygen, and so they start driving ventilation. Okay, you will continue to hyperventilate as long as you stay at high altitude. Okay. So this hyperventilation causes respiratory alkalosis. Okay, you're blowing off CO2, the arterial PCO2 drops, okay, and as a result, the pH goes up, you become alkalotic. The kidney starts compensating within a day, and within a week or a week and a half, you may have recovered from this. Okay, this respiratory alkalosis, okay, lowers arterial PCO2, and that inhibits the central chemoreceptors. Okay, so you go to high altitude, peripheral chemoreceptors say, breathe faster, so you do, you blow off CO2. Central chemoreceptors say, wait a minute, the CO2 is lower than it should be, let's not breathe so fast. So the central chemoreceptors are fighting against peripheral chemoreceptors, and until they have adapted, this competition continues. The peripheral chemoreceptors sort of dominate in that they maintain elevated ventilation, but the ventilation is probably a little bit higher after the central chemoreceptors adapt. Okay. Well, so what good is hyperventilation? Well, of course, you need to get a certain amount of oxygen into your body, to your cells, and so there's the obvious benefit of hyperventilation, increasing the oxygen supplied to the tissues. Another arguable benefit is that by blowing off CO2, you make more room in the alveoli for oxygen, and this undoubtedly happens, but how significant it is, so the alveolar PCO2 goes from 40 to 20. Okay, so that's a little bit of space, and you get a few milliliters of oxygen more that way. Okay, so peripheral chemoreceptors never adapt. You are always going to be hypoxemic at high altitude, and so you will continue to hyperventilate. Okay, next response is polycythemia. Okay, now you breathe low oxygen, you are hypoxemic, and hypoxemia stimulates the kidneys to produce erythropoietin, also known as hemopoietin. Okay, and this is a stimulus for the bone marrow to produce more red blood cells. Okay, so polycythemia means that you have an increased amount of red blood cells and an increased amount of hemoglobin in your body. Your hematocrit will go up, your hemoglobin concentration will go up. And this response takes kind of a week, a couple weeks, 3 weeks, but it depends on how high up you go. Okay, now one study said that the maximal level of red blood cells, or the maximum hematocrit, is reached at 11.4 days times the altitude in kilometers. So if you go up 1.5 kilometers to Denver, that would take maybe a couple weeks. If you go up to higher altitude, it might take 3 or 4 weeks. Okay, so it's going to take a while. Okay, well, so what good is polycythemia? Well, this increases the capacity of the blood for oxygen. And the oxygen capacity, you recall, is 1.34 times grams of hemoglobin. Okay, so miners who live and work in the Andes Mountains of Peru, on average, in one study, had 18 grams per deciliter of hemoglobin. Their oxygen saturation was only 81%. Yours is 97 or 98%. Theirs is only 81%. But because of the greater amount of hemoglobin, their oxygen content of arterial blood was 22.4. So that's a couple milliliters greater than what yours is, even though you're at a higher level of saturation. So this increased oxygen capacity is clearly beneficial, and it will persist as long as you're at high altitude. The main downside that I could see is that the blood becomes more viscous, and this means that it will be a little bit more difficult to pump it through the blood vessels. So it might be a little bit more work for the heart. Now, Olympic athletes, especially long-distance runners, may like to have an elevated hemoglobin content because this gives them a competitive advantage. It increases the oxygen capacity of their blood. And so they can go and train at high altitude and increase their hematocrit. What they're not supposed to do is blood doping, which is taking their own blood and concentrating the red cells and shooting it into their blood just before they compete. Okay, so that's the second change. The third adaptive response in high altitude is a right shift of the oxyhemoglobin dissociation curve. Okay, and this is the result of 2,3-diphosphoglycerate. At high altitude, this is increased by breaking down of proteins in red blood cells. And just like in the systemic circulation, if you shift the oxyhemoglobin dissociation curve to the right, this facilitates oxygen unloading to the tissues. Okay, and so this is going to be a beneficial result at high altitude. It is, however, useful only if you go up to a certain point. If you go to extremely high altitude, this will become counterproductive. And so we can see that situation in the case of two people who managed to climb to the top of Mount Everest without supplemental oxygen. And until they did this, every respiratory physiologist would have told you this is impossible, nobody can do this. But they did it. And barometric pressure is 253. Their alveolar PCO2 was 7.5 instead of 40, it's 7.5. Their arterial pH was 7.76. It's extreme respiratory alkalosis. They're hyperventilating like crazy. Their alveolar PO2 was 35. Their arterial PO2 was 28. Okay, so it is possible to do this, at least for a while, and live. Okay, now, if we think about high altitude, okay, let's say this is the normal oxyhemoglobin dissociation curve. Okay, usually a right shift is good because it means more oxygen unloaded to the tissues. But, well, let's first see if, oops, okay. But if we remember these guys who went to the top of Mount Everest where their alveolar PO2 was 35, okay, so if in the lungs the PO2 is 35, and this is our oxyhemoglobin dissociation curve, we're only going to get about 20% saturation of hemoglobin in the lungs. Okay, so this is not very good. If we were to have a left shift of the curve, which is shown here, then at the same PO2, we'd be up here around 70 or 80% saturation. Okay, so if you want to function at extreme high altitude, this right shift is not a good thing. At moderately high altitude, it is a good thing. Now, these curves are actually measurements of bird populations that live chronically at very high altitude, and they have evolved a different form of hemoglobin with a higher oxygen affinity, and this is what they need because they live at extreme high altitude. So our hemoglobin works from sea level up to maybe 1 or at most 2 miles above sea level, and higher than that, you need to start thinking about getting a different kind of hemoglobin. Okay. The final response to high altitude is hypoxic pulmonary vasoconstriction. Okay, this is a response to alveolar hypoxia. You have low PO2 all throughout your lungs, so you have generalized hypoxic pulmonary vasoconstriction. At sea level, this response is very useful because if you have a poorly ventilated part of your lung, you want those blood vessels to constrict because that will reduce blood flow there and force the blood to flow through better ventilated parts of the lung, and you want the blood to be matched up with the oxygen. Okay, but at high altitude, this happens throughout the entire lung, and as a result, you have pulmonary hypertension. Okay, and this is why a very common feature of acute mountain sickness is pulmonary edema. You're increasing the pressure inside the blood vessels in your lungs, so the hydrostatic pressure is greater, the osmotic pressure pulling fluid back in is not changed, and so the result is you get edema. Okay. Another consequence of hypoxic pulmonary vasoconstriction is right ventricular hypertrophy. The right ventricle has to pump blood into a higher resistance vasculature, and so it has to do more work. Okay, if you do an autopsy and look at a cross-section of the heart from somebody who lives and works high in the mountains in Peru, they will have much thicker right ventricular walls than a person who lives at sea level. Okay, so pulmonary hypertension, pulmonary edema. Okay, so about the only good thing that anybody has been able to figure out for having generalized hypoxic pulmonary vasoconstriction at high altitude is that this would tend to cause more uniform perfusion of the lung. Okay, and if you remember, we said that at the very top of the lung, due to gravity, perfusion is practically zero. Okay, but at the top of the lung is where the VQ ratio is the highest and where you have all kinds of oxygen. So if you get more uniform perfusion of all the lung, then you get more blood flow through the top of the lung where there's the highest VQ ratio. Okay, so that's the responses to high altitude. And this is a really interesting study published a few years ago, and they looked at women in Tibet, which unfortunately no longer exists. But anyway, Tibetan women live at 4 kilometers elevation. And when they looked at the hemoglobin, the saturation of their blood with oxygen, they found that there were 2 groups. One had normal oxygen saturation. Okay, that's this column here, and the other had high oxygen saturation. Okay, and the mechanism isn't quite clear, but this is a genetic inherited trait. And so in this study, they looked at the survival of infants from mothers who have normal oxygen saturation and high oxygen saturation. Okay, so the number of, okay, well, let's back up a second. Okay, the number of pregnancies, 4.6, 4.8, is the same. Number of live births is about the same. Oops, going the wrong way. The number of children now alive was only 1.6 for the normal mothers and 3.8 for the high oxygen saturation mothers. Okay, and the reason for this, of course, is that 40% of live births with normal oxygen saturation died in infancy, and only 6% of the ones with high oxygen saturation. Okay, so clearly this shows that human evolution is happening today. The women with the phenotype of high oxygen saturation produce infants who survive, and the ones with normal oxygen saturation die. And so gradually this trait will increase in this population, or it would if China hadn't kind of eliminated Tibet. But, you know, people still live there. Okay, well, this was real. I thought, well, clearly they're looking at a different type of hemoglobin. And so I wrote to the author, Cynthia Beale, and asked her about this, and she said that this was not the case. That they don't really understand the mechanism, but there is another population in Ethiopia with high oxygen affinity in the blood where they think that maybe it is a new form of hemoglobin. Anyway, okay, that's the end of high altitude. Now we'll talk about absorption atelectasis. And this is maybe the first example where nitrogen is actually doing something useful for you. Okay, it's always there, it's the dominant gas, and yet it just sits there mostly. But sometimes even that is a good thing. Okay, so let's take a person breathing normal air. Their alveolar PO2 is 100, PCO2 is 40, water vapor is 47, and the rest is nitrogen. Total pressure is 760 torr, so I guess we're at sea level. Okay. Now, let's say there's an airway obstruction, a mucus plug blocking up the access to this alveolus. Okay, so what's going to happen is the VQ ratio has gone to 0, and so instead of the blood gases equilibrating with the alveolar gases, gradually the alveolar gas will change to be whatever is in the venous blood. Okay, so the PO2 is now 40, CO2 is 45, water vapor is 47, that's the same, and nitrogen is also the same at 573. Total pressure is 705. Okay, so the pressure decreased, the total pressure decreased, the alveolus will shrink down a little bit, but less than 10%. So it's not a big deal. You'd rather it didn't happen, but it's not a huge thing. Let's say you have somebody breathing 100% oxygen, okay? If they're on 100% oxygen, CO2 is going to be 45, water vapor is unchanged, but eventually they blow off all the nitrogen from their lungs and replace it with oxygen. So total pressure is still 760, but now they get an airway obstruction. And now the alveolar gas gradually becomes what is in the venous blood. So we have a PO2 of 55, 45 CO2, a little bit of water. Total pressure is 150, so this is less than a quarter of the total pressure. The alveolus will shrink down to a very small volume, and it's likely that it's just going to collapse altogether. Okay, this is called atelectasis, and it's due to the oxygen being absorbed by the blood when there's an airway obstruction. Okay, and so this is absorption atelectasis. So the fact that we have nitrogen in the air means that when we have airway obstructions, which happen all the time in normal people, we don't tend to get absorption atelectasis. Okay, and so this is kind of called a nitrogen splint mechanism. The nitrogen being there just keeps the alveolus from collapsing. And it's also, a reason that you probably want to increase the FiO2 some if they need more oxygen, but don't go all the way to 100% oxygen. Okay, now we have deep sea diving, which is what happens every week in Sea Hunt. And if you are insomniac and you're awake at 2 in the morning, you can watch Sea Hunt on some channel number 487 or something. Anyway, where Lloyd Bridges does scuba diving, and he has this nice tank of compressed air, and the compressed air, he goes to a tube and he breathes through this tube the compressed air. So if you go 10 meter, well, if you're standing on the shore of the ocean at sea level, the pressure of miles and miles of air over you is 1 atmosphere, okay? 760 torr. If you go 10 meters below the surface of the ocean, the total pressure increases by 1 more atmosphere, so now the total pressure is 2 atmospheres. Okay, if you're breathing compressed air, what's going to happen is that at 10 meters, you're going to have twice as much nitrogen and twice as much oxygen because you're breathing air at 2 atmospheres, okay? Now, what will happen is the partial pressures of all these gases will increase in your blood, and gradually the gas diffuses to your tissues, the partial pressures will go up in your tissues, and your entire body will be functioning at 2 atmospheres, okay? If you go even deeper, you'll be at 3 or 4 atmospheres. Okay, now if you're deep under the surface and you come rapidly to the surface you will get decompression sickness. Okay, and this is also called the bends, at least that's what they call it in sea hunt, or caisson disease. Anyway, what happens is that you have all this dissolved gas in your body, and you rapidly come up, the pressure decreases, and the gas comes out of solution, forming bubbles. Okay, if the bubbles form in your joints, this is supposed to be very painful, and so people move around in weird ways, and that's why it's called the bends. I've not actually seen this in real life, so I can't visualize it, but anyway, and it's the same principle as opening a bottle of champagne. You have the champagne is saturated with dissolved carbon dioxide. The cork pops, the pressure decreases, and the CO2 comes out of solution because it's only in solution because it was pressurized. Okay. Anyway, so the same thing happens. Bubbles come out of solution. They form in your joints. If they form in blood vessels, this is really a bad thing. They can occlude a small artery. And if this happens in your heart or in your brain, it can be pretty severe. Okay, so you can avoid decompression sickness by not rapidly ascending from deep under the ocean. Okay, and so if you keep the ascent rate to 10 meters per minute, then you're probably safe. The treatment for decompression sickness is recompression. Put somebody in a hyperbaric chamber, if you can. Okay, let's see. Okay, well, if you like novels, an author that I like is Nevada Barr. She writes about a national park ranger, a female protagonist. And in A Superior Death, she's working on Isle Royale in Lake Superior, and this involves some shipwreck under the surface, and she has to do scuba diving, and there's a nice description of the bends and how stopping every 10 meters and waiting a couple minutes so that you don't get the bends. Anyway, yeah. So another thing that can happen with scuba diving is nitrogen narcosis. This is also called rapture of the deep, and this is apparently a kind of narcosis that happens as a pharmacological response to high partial pressures of nitrogen. Okay, it usually occurs if you're at 100 feet or more below the surface. Okay, so that would be 4 atmospheres. And I guess the partial pressure of nitrogen would be greater than 3,000 torr. And this is a pharmacological effect. The Navy has divers that go much deeper than this, and they use helium instead of nitrogen in their compressed air tanks because they don't want people their divers having too much fun under the surface. It prevents nitrogen narcosis. But helium is also less dense and less soluble than nitrogen, and so less problems for that reason. Let's see. Okay. Another thing you can do at the ocean is snorkel breathing. Okay, now when you're doing scuba diving, you're breathing compressed air, and the pressure inside your body is the same as in the water outside. In snorkel breathing, you breathe through a tube that goes up above the surface, and so the air that you're breathing is at sea level, pressure, 760 torr, and the air inside your lungs is, it's at will be at the same pressure. Yes, that's true. Okay, now, so the lungs are at 760, but your body is under the water, and the water pressure is compressing your thoracic cavity. Okay, so as a result, you have to do a lot more work to expand your lungs because you're working against this greater pressure, and FRC will be reduced because at FRC, you just relax your muscles and the water squeezes your thoracic cavity to a small volume, but the pressure inside is 760, the pressure outside is 760, but it's mostly up, it's above the surface of the ocean. Well, so With snorkel breathing, you're breathing through a tube. You don't want the tube to be too narrow because of Poiseuille's equation. A narrow tube would have a high resistance. It would be hard to move air through it. You don't want the tube to be too wide or too long because the tube is acting as dead space. And so you want to get air all the way from outside the tube rather than just moving back and forth through the tube. You can overcome this if you breathe in through the tube, but you blow out into the water like that. But even if you do this, the maximum depth that you can reach is just 3 or 4 feet under the surface, about 1 meter, and the limiting factor is the hydrostatic pressure compressing your thoracic cavity, making it difficult to inflate the lungs. Okay, now immersion diuresis is something, if you immerse someone up to their neck in water, they tend to urinate, and that's all I will say about that.